All right. So basically the idea is this when we talk about if vectors are dependent. If vectors are dependent, let's state it in the 2 by 2 case, in the R2 case. If two vectors are dependent, then that means one is basically a copy of the other. It may be stretched a little bit or in the exact opposite direction. We'll just say stretched so we don't always have to keep adding that caveat. But if two vectors are dependent, then that means one's just kind of a longer version of the other. So it's like they're the same thing, right? There's no new information there. On the other hand, if two vectors are independent, then that means they are two different vectors. They both contain two different pieces of information, and therefore, we need them both. With two dependent vectors, we don't need them both because one's just a copy of the other, so we don't have two different pieces of information. All right. So when we move to larger Rn spaces, larger R spaces, when we move to say R3, the idea is still the same, but it's kind of booted up in terms of working in 3 dimensions. But don't think about it that way. What you need to do is just realize, if two vectors, whether we're in R2 or R3, if vectors, we won't even say two vectors, if vectors are dependent, then that means they are kind of, at least one of them is kind of a copy of the other two, or is some combination of the other two. All right, so that's the idea when we talk about determining if vectors are what it means to be dependent or independent. We like independent vectors because that means they each contain new and specific information that is vital. Okay, with dependent vectors, that's not the case. Some are basically copies of the other. So when we talk about R3, let's move to R3. So here's 3 vectors, and the question is, are they dependent? Are these independent or dependent? Okay. Conceptually, it means if they're dependent, that means one of them is kind of a combination of the other two and so is redundant. If they are independent, then that means they are each 3 separate individuals. I can't use 2 to build the third one. Okay. So, but with that being said, in order to answer this question, the problem is still the same, essentially. I need to solve this equation. A times U plus B times V plus C times W equals 0. So you notice it's the same equation we solved before, but now it's just involving the 3 vectors. So if I was involving 4, you would have a 4th term there, but it's the same thing. So it boils down to being able to solve this and determine if 0 is the only solution or not, right? So from here on out, it's just a lot of kind of algebra. So 1, 2, minus 3, right, representing U as a column, plus B times 3, 1, minus 2, plus C times 5 minus 5, 6, equals 0, 0, 0. And of course that leads us to this system. I'll continue to write it out for the next little bit just because I think it's important to see how we get where we get. If you think about what it takes to add vectors, remember how it works. You add this component to this component to this component, right? So you're going to have A times 1 plus 3 times B plus 5 times C, and that's supposed to equal this component, 0, right? So that leads to that equation. We do the middle components, the second components, we get A times 2 plus 1 times B minus 5 times C also equals 0. And the bottom components, the third component, give us this. So that's the system we want to solve. And we've learned how to solve these. Let's go maybe the most direct route here. If I were wanting to solve this and I had technology at my fingertips, I would probably just go this approach, right? Create the augmented matrix and then find the RREF of it, right? Reduce it. Now I'm not going to do it by hand. I'm going to use technology because we've already practiced doing this by hand. So, okay, so what we learn here, there's the row reduced echelon form. So notice we have a free variable right here, right? Because there is no leading entry in that row. So that's a free variable. And remember, if you have a free variable, that means there are an infinite number of solutions, right? Or if you want to, there's another thing you could say is if you have an entire row of zeros, there's an infinite number of solutions, right? Okay. But we have an infinite number of solutions. 0, 0, 0 is one of them, right? Because 0, 0, 0 was always going to be a solution. But an infinite number of solutions, so we can simply say that these vectors are dependent. So infinite solutions to this system. So U, V, and W are independent. That means they're not all unique pieces of information. Okay. So another way to think about it is it would be possible for me to just use two of them, to find create a combination of two of them to get the third one, right? So let's just let me show you what I mean by that. So if I continue to actually find the solutions and say, all right, I know that C, right, our solutions are A, B, and C. That's what we're looking for. And we know C is a free variable, so let's call that T. And then we just do some back substituting right there, right? B plus 3T equals 0. So that means that B equals negative 3T. And then back substitute up top, A equals 4T, right? So as long as I choose T freely, that's going to give me solutions. Obviously 0 yields 0, 0, 0. We knew that was always going to be the case. But if we let T equal 1, then we get the solution. Then A, B, C equals 4, negative 3, plus 1, right? So what that means is 4 times U minus 3 times V plus 1 times W equals 0, right? That's what we just found. Here's the interesting thing. If I just do a little algebra on this, W equals negative 4U plus 3V. So look at that. Remember how we said these are, wow, some of you have been screaming at the screen for the last 5 minutes, right? You're saying, no, I'm confused. I really apologize. Welcome to live TV. These are dependent, right? If they're an infinite number of solutions, they are dependent. Okay? So what we've just shown here is W is a combination of U and V. W is not unique. It's just a little bit of U and a little bit of V. So it doesn't tell me anything. Likewise, I could say that about any one of them. So W could be built using negative 4 U's and 3 V's, or let's say 4U equals 3V equals or minus W. So U equals 3/4 V minus 1/4 W. So I can build U using 3/4 of V and minus 1/4 of W. Right? So again, this is what it means to be dependent, is I can take one of the vectors and build it out of the other two. So like in this case right here, I don't need W. I would just use this in its place. I could just use U, V, and then minus 4U plus 3V. Okay. Now, graphically speaking, what that means in 3 dimensions, right, is one vector heads this way. Well, let's do it this way. One vector heads this way, and the other vector heads this way. Now, here's what I need you to imagine is, and we'll do a graph of this. Well, let's I am not gonna torture you with my graphs. Let me show you what it means using a good quality graph. In other words, using GeoGebra. Okay, so this is what we've got. I have graphed the vector u and, let's try that again, the vector v. All right, the vector u and the vector v. Okay, so no big deal. We've got it right here. U is the blue one and V is the red one. Now here's a fact that you'll want to remember is if I have any two vectors, I can get a plane that contains them. So look, I'm going to draw this plane that goes through those 3 points. And notice it goes through those two vectors, right? Any two vectors define a plane. So that's what we got, u and v. And you can see u and v are clearly independent, right? They are headed in different directions. Okay, so let me add to this vector w. All right, so w was 5 minus 5, comma 6. There is w. Okay, it sure looks like it's headed in a different direction. Let's color it a different color because we can. Bam. But here's what I want you to notice. I'm going to rotate this a little bit. Remember, these are dependent. We just determined that. Look what happens. Look at that. The green vector, w vector, is in this same plane. So that means I can take a little bit of u and a little bit of v. So I can take negative 4u and 3v, and I can get w. So see, I can build w using those two. So graphically speaking, when we move to three-dimensional dimensions, if three vectors are dependent, that means they lie in the same plane. Okay. Let me give you just an example. Here would be a vector that is independent of u and v. Look at it. It doesn't lie in the plane. So it contains its own unique information. I just made that one up. So, but there you go. So, that is the idea of how you find vectors, the dependence of vectors. Okay, so take a look at this. For the 3 by 3 case, you can see it's the same idea, and for larger cases as well. All right, now here's a couple terms that you're going to need to know. Well, we'll wrap this one up, and we'll do one more wrap up video with the last little odds and ends.